Welcome. I'm going to talk about stainless steel. Stainless steel is very extensively used in industry. Stainless steel is used for its superior corrosion resistance. Where corrosion is a serious problem, stainless steel becomes a great choice. For example, stainless steel is used extensively in paper machinery. Stainless steels are used in food industry, in many other application. Stainless steel pipes are used for petrochemical industry, chemical industry. Stainless steel pipes are used. I was quite fortunate in my career to work with various grades of stainless steel. In paper machinery, when we were making the machines that makes papers, we used to use stainless steel SS304 and 316L extensively because there used to be huge exposure to chloride environment. So stainless steel SS316L grade has got extra low carbon content as well as molybdenum, which makes it very good a choice for using in applications where chlorine or pitting, those kind of things are a risk in service. I have also used 317LN, 347, 321. These are stabilized grades used in chemical industries extensively. So this is something that I thought it could be an interesting thing to make a learning resource for you to gain from this shared experience. So let's dive in. Sometimes I feel steel making is like a cooking process. When you cook, for example, biryani, let me give an example of biryani. So rice is the main ingredient, and with that you add salt, you add pepper, you add turmeric powder, you add chili, you add ginger, you add garlic, cinnamon, and so many other things, and each one of them brings some goodness and it makes a fantastic biryani for you to enjoy. Steel making is very similar in many aspects like this. Stainless steel is a ferrous material, means that is, of course, iron is there. But what makes stainless steel is chromium. Let me tell you why stainless steel are used because of its corrosion, resistance to corrosion. So corrosion is a problem in metal industry. We use stainless steel where coating is not a good solution, but stainless steel is very expensive. So this cannot be used in every application. So there are alternate way to prevent corrosion or oxidation. So corrosion is a big enemy for metal industry. For example, carbon steel. And oxygen is not very good thing for steel because oxygen with some amount of moisture makes it an ideal situation for corrosion. What is corrosion? Actually, ferric oxide, ferrous oxide, Fe2O3, Fe3O4, these are all iron oxides. So iron and oxygen, when they mix, they become basically rust. Hematite, magnetite. These are kind of iron ore, basically iron in oxidized form. In other words, if I say iron is an unstable element and which wants to get stability when it gets mixed with oxygen. So an iron ore is more stable than iron because it is already corroded. So when the iron is refined and you make steel, then the surface is exposed to the air and moisture, so they start to corrode. So corrosion will start, rust will fall. So as engineer, to protect those equipment from corrosion or rusting, you apply paint. The paint creates a barrier, it sticks to the body of the material, of the metal that is you are trying to save from corrosion. That paint layer or fusion bonded epoxy, you can use 3-layer P coating, you can apply any type of corrosion prevention coating that you are giving, that actually creates a subverting barrier, not allowing the oxygen to come in contact with the metal, and that's how they prevent corrosion. Where stainless steel, because of its cost, is not a suitable solution. For example, you cannot make a cross-country pipeline for gas, transportation of gas using stainless steel. This is not feasible. You are going to use carbon steel for sure. So you are trying to make sure they are less prone for corrosion. So you add elements to reduce corrosion and also protect it from either internal coating or external coating. That's how corrosion is prevented, rust formation. This is how we safeguard material and facilities from corrosion. But stainless steel uses that oxygen to protect itself. So the oxygen, which is so harmful for normal carbon steel, is used to form chromium oxide, which creates a thin film on the top of the material that makes stainless steel. Now, stainless steel is 10.5% chromium minimum or more. Once you add in steel, that becomes stainless steel. There will be different percentage of chromium and other alloying elements like nickel, like molybdenum. Those things are added for specific purpose to change the property. But essentially, chromium is what makes stainless steel. And it is chromium oxide that is formed at the surface is preventing further oxidation. So now let's dive in. And then there are different alloying elements. You will find nickel is added. You find molybdenum is added. Of course, carbon will be there. In stainless steel also carbon is there. So carbon has got good benefit and also adverse impact on the welding and the material. So in next few minutes, I will take you through this presentation slide where I have structured and compiled some of the information which will be very useful for you to understand and revise at times so that you don't forget. Let's dive in and see. Metallurgy sometimes is a subject which looks dry, but really it's very, very interesting subject. As I said, it's like cooking. So I will give you the example and try to explain the effect of various elements in a very logical manner. So it will be interesting for sure. Let's dive in. So here is my presentation. Stainless steel and impact of alloying elements. What is stainless steel? Stainless steel is a group of iron-based alloy known for their high corrosion resistance. I mentioned they are good for corrosion resistance, strength, as well as durability. Now, stainless steel contains, as I mentioned, 10.5% or more chromium, which forms a passive layer of chromium oxide, Cr2O3. This is called chromium oxide on the surface of the material that prevents rust and further corrosion. So chromium is the backbone in stainless steel. That's most important element. Now, what is the impact of carbon in mechanical properties and the properties of stainless steel? See, this picture shows this is a weld performed in stainless steel, and you can see intergranular corrosion, and that is in the heat affected zone. Adjacent to the weld is the heat affected zone, and see the corrosion that has happened. So this intergranular corrosion is caused greatly by carbon, effect of carbons. I will show what is the benefit of carbon steel first. Now, carbon, what is the benefit of carbon? Now, one thing is very important for you to know. Carbon is like salt. If you give salt, then you find it very tasty. You can add a little bit more, but beyond certain point, it becomes too difficult even to eat. It will spoil the whole thing. Therefore, carbon is something like this, a very small proportion, small amount of carbon, 0.01, 0.02, 0.03%. That itself adds huge amount of strength and also gives hardness, which you of course need. But carbon has got a very strong impact, adverse impact on ductility. It reduces ductility and it increases hardness. Now, if increases hardness in the heat affected zone, the material becomes more brittle. So they become susceptible to cracks and of course distortion and poor welding fusion and penetration. So it becomes difficult because it's very hard. Hardness will increase and then it has got ill impact on direct. Now it has got much more severe impact, which I am going to show. This phenomenon is called weld decay or sensitization. Now, see, this is a stainless steel. These are grain boundaries. Now, chromium is there. Normally, as I said, 10.5 plus. Normally, you will find chromium can be as 20-22% in steel. Carbon steel, in 304, in 316, you will get 18 to 20%, 22% at that range, chromium. So very high chromium. And you need minimum 10.5%. Now, what happens when the weld deposit starts cooling down at certain temperature around 800 or below to 400, 450, at that range, the carbon combines with chromium and it forms chromium carbide, Cr23C6. This is called chromium carbide. So this chromium and carbon mixed together forms chromium carbide, and that drains out. The chromium loses its property because this is a depleted chromium depleted zone now, and this chromium carbide gets deposited, settles in the grain boundaries, and around this area you are actually losing, or the chromium percentage is significantly depleting, and that causes intergranular corrosion. That is more profound in heat affected zone. So weld decay is a phenomenon in stainless steel which is actually refers to intergranular corrosion that occurs in mostly in the heat affected zone, the picture I have shown, due to sensitization. And what happens, chromium carbide precipitates at that 450 to 850 at that temperature, and then this precipitates in the grain boundary, and this takes away the typical property of chromium, and this boundary drops below 10%, and the corrosion resistance is gone. And this also gets enhanced with aggressive environment like salty environment, fluorine rich environment, or aggressive environment. And that's what is called weld decay. This is very common in 304 and 316. Now I will talk about a little bit what is the remedy for this. Now just imagine there is a very interesting strategy. Now in 316 grade stainless steel, you have carbon percent approximately 0.08%. So now if you have got these percentage of carbon, that will come in contact with the chromium from chromium carbide, and that takes away the chromium. Now if you reduce the percentage of carbon, then there is less carbon to act with chromium. So the development in the steel made it possible to bring the carbon percentage to almost 0.02 or 0.03%. So this comes with a designation L, stands for low carbon or extra low carbon stainless steel, where typically 0.03% is the maximum limit. Now from 0.08, you brought it down to 0.03. So 0.05% of carbon has been reduced. So we lost some strength, which will be compensated with something else. But here the bigger problem is weld decay and stainless steel losing its own property just because carbon is doing a havoc. They're falling in love with chromium and they get married, and the rest of the world is going to hell. Something like this. So you bring down L, bring down the carbon percentage to 0.03%. This is called L grade. Something more is done. In stabilized grade, now 321, for example, these are called stabilized grade 347. 321, you add some other alloying elements. So what happens? For example, titanium is added in 321 or niobium is added in SS347. So what happens? These niobium and titanium binds with carbon. So niobium and titanium gets combined with carbon and not allowing this carbon to react with chromium. So chromium is intact. The moment chromium is intact, the stainless property remains intact. So these are called stabilized grade. And also post-weld heat treatment is also done to dissolve the chromium carbides that might have precipitated in the grain boundaries. And also rapid cooling. Now, just imagine chromium carbide is forming around 450 to 850 around this temperature. So when you are cooling down, the steel gets cooled down from welding heat. What will happen? They will gradually cool, and this gradual cooling will allow carbon and chromium to mix together and form chromium carbide. And as they cool down, they precipitate in the grain boundaries and starts intergranular corrosion, and that's how the whole thing gets spoiled. If you suddenly cool, very rapid cooling, which is called quenching, then what happens? There is no time for the chromium and the carbon. There is no time for the chromium and carbon to react, and the cooling happens so rapid that there is no chance for the chromium and the carbon to form chromium carbide. By doing that, the property remains intact. So rapid cooling, which is called actually solution annealing, is done for stainless steel from 1100 degrees centigrade. They're quenched in water, and that process is called solution annealing. And that's how we are going to talk about solution annealing. Is at a high temperature heat treatment where 1000 to 1100 degrees Celsius. You take the material, stainless steel, and from there rapid cooling by quenching, often in air. Mostly it is done with water, and stainless steel is solution annealed to improve its corrosion resistance and mechanical properties, microstructural uniformity, as well as after forming or welding. So in the steel making process, when after hot rolling and to remove the stress from cold working as well as from hot working like welding, they are subjected to solution annealing. So this heat treatment dissolves unwanted precipitates like chromium carbides, as we mentioned, and it restores the steel full corrosion resistance and also relieve the residual stresses. Now, I'm going to give you some more alloying elements and their impact. For example, I'm going to talk about now nickel. Now, nickel is a very highly desirable element. It is nickel chrome are very, very common. So chromium percentage is higher always. Always remember, chromium is what makes stainless steel. So it's always more than the nickel percentage. Now, nickel percentage around 8 to 10% or more depending on the material grades. You don't have to remember this percentage, but you have to develop an understanding and refer the relevant standard. So for 304 is like 18.8. So 18% chromium, 8% nickel, around this range. 18 to 20% chromium, 8 to 10% nickel. That's what is typical 304. And in fact, 316 also has this similar chemical composition with respect to chromium and nickel. So it enhances the structure and the ductility. It retains the austenitic phase. These are austenitic stainless steel. 304, 316 are all austenitic stainless steel. I will show you from the Schaeffler diagram. There are certain areas, ferrite, martensite, austenite, austenoferrite, again, fully ferrite, so austenite, martensite, ferrite, different zones are there. So you will find these are various phases. So I will show you from the Schaeffler diagram where actually these stainless steels are falling. These stainless steel grades are falling within the Schaeffler diagram. You will have a very clear understanding. So it retains the austenitic phase and make the steel magnetic and tougher. nickel enhances the toughness of the stainless steel and also formability and weldability. It's good for weldability. It also gives strength, as I said. And you don't add carbon percentage so much to get strength because you are compromising with the stainless property because it starts reacting with chromium. So you reduce the carbon percentage, but you have to gain the strength. So nickel adds that strength as well as it doesn't affect the weldability. It improves the weldability. Now I'm going to talk about a very interesting element called molybdenum. In fact, molybdenum, when 2 to 3% is added to SS304, then we get 316. So SS304, stainless steel grade 304 and 316 has got almost identical composition, excepting 316 has 2 to 3% molybdenum. Now, what this molybdenum does? Molybdenum is actually, it gives exceptional resistance to localized corrosion and pitting. So it gives extra, it helps prevent pitting, particularly in chlorine or chloride rich environment. It also enhances the creep property. It enhances the strength and hardness, particularly at high temperature. We call it creep property. Now I'm going to give a small brief comparison of the three main alloying elements. Chromium, it forms the passive film, and general corrosion resistance it brings because it is preventing further corrosion. Nickel, it stabilizes austenite, enhances the ductility, the ability to form, improves the toughness, ability to absorb shocks, yet formability, so that you can give shapes. So ductility and formability are two very important aspects which comes from nickel. And molybdenum gives resistance to local corrosion attacks such as pitting or crevices, and that's what is added particularly in chloride rich environment. So this is added to 304 and you get 316. Now, as we mentioned, to reduce corrosion further, you have to reduce the carbon percentage to extra low level. I have given this presentation like a storytelling mode. Try to remember that it's not taxing your brain and getting panicked. What is the importance of nickel, chromium, molybdenum, vanadium, and stuff like that? What carbon does? Try to understand logically. Carbon gives strength, so you will get more strength with carbon. So 304 and 316 has got higher percentage of carbon, 0.08. Low carbon grades will have 0.03%, say maximum. So since the carbon is less, L grades will have less strength. So you will find mechanical property, tensile strength is lower than 304 because it has got L, low carbon, extra low carbon, and carbon gives strength. So since carbon percentage has been reduced, so 304 has got superior mechanical strength compared to 304. But see, this is 0.03% and it is 0.08%. 304 contains 0.08%. Chromium is 18 to 20 and nickel is 8 to 10.5%. So now these percentages do not change much. Only thing is carbon percentage is reduced in L grade. Very easy to remember. And now if you see here, there is a percentage of molybdenum, 2 to 3%. So 304 does not have molybdenum. That's the main difference. And this is not there in this grade 321 and 347 because these are titanium stabilized. So titanium has been added in 321 and niobium is added in 347. So there is no molybdenum in these two grades. Now corrosion resistance, good. But 304L with lesser carbon percentage, it will have superior, better corrosion resistance. Of course, 316 is superb because it has got better corrosion resistance, because it has got molybdenum also, and it has got extra low percentage carbon as well. Now, if you see, slightly lower than 316, because L grade will have slightly less tensile property. So with this understanding, you can see where they should fall. Now, if I am asking what makes 316 and 304 different, molybdenum 2 to 3%. What makes L grade to standard grades? Carbon percentage, 0.03 maximum in L grades. Otherwise, it is almost 0.08% everywhere you can see across. Chromium 18 to 20, around this percentage everywhere. Nickel 8 to 10%, around this range across, slightly more or less. So this is how you can compare. And others, with the stabilizers added, the stainless steel becomes more expensive. Now, if you look at the cost, the 304 is the cheapest of the stainless steel grades, and these are the stabilized grades are more expensive, and L grades are more expensive because you need more controlled steel making process to keep the carbon in the lower side of it. Now, in another discussion, I talked about welding, a selection of electrode with carbon steel to stainless steel. We talked about dilution. We talked about how to use Schaeffler diagram and how to find electrode for carbon steel to stainless steel. So very interesting. I encourage you to go through this. And now I'm going to show you the few of the common stainless steel types, austenitic stainless steel. So this is called Schaeffler diagram. So nickel equivalent is here. This is a formula given for nickel equivalent. This is on the horizontal axis. You have got chromium equivalent. So this percentage of nickel, chrome, moly, all these once you add, so you get a nickel and chromium equivalent. Based on that, you can place those stainless steel grades in this diagram. Now, this zone is first zone within a 6% nickel equivalent, and 2% is ferrite martensite. Then we get martensite, then austenite and martensite, then austenite. So austenitic stainless steel will be above this point for sure. Now 316 is austenitic, 304 is austenitic. So they will be beyond this line for sure. Now this is 0% ferrite, and then 5%, 10%, and below this line where you can see 446, it is all ferrite. So when we are talking about austenitic stainless steel, these are non-magnetic. All right. And excellent corrosion resistance. So 316, 347, 321, 310, 316, 316L, 321, 347, 309. These are all austenitic stainless steel. They are non-magnetic and excellent in corrosion. So the next comes ferritic. Now, where is ferrite? This is ferrite. So 430 is here ferritic. Ferritic stainless steel are magnetic. So in NDT, there may be a question that 430 is the stainless steel. Can you do magnetic particle test? Yes, you can, because this is magnetic. But SS304 is non-magnetic. So magnetic particle test cannot be done as a non-destructive testing method. For such kind of application, you have to do penetrant test most likely. So this is how you decide. So it is a ferritic stainless steel 400 series is magnetic, used in automotive trim, appliances and all that. Then comes martensitic. Now anything above this area is martensite. So 410 here is martensite 420. This will all come in this region where this is martensite. Now it's again magnetic. Ferritic and martensitic are magnetic. How to remember? Martensite magnet, ferrite magnet, austenite is non-magnetic. Ferrite and martensite is magnetic. Austenite is not magnetic. Remember, austenite is non-magnetic. Martensite magnetic. Ma martensite, Ma magnetic. This is how you can remember. And also ferrite. Ferrite is also magnetic. Moderate for corrosion resistance. They are used for knives, turbine blades, etc. And last is the duplex one. Extensively used in industry, petrochemical, oil and gas industry. They are mixed austenitic and ferritic structures. So this area where it's beyond 0% ferrite, 5%, 10%, 20% ferrite, and above this austenite, above this line austenitic region and ferritic. So duplex stainless steel are having these two phases. One is austenitic and ferritic. They are very, very high strength as well as great in corrosion resistance. And they are also non-magnetic. That's all about it. I hope the discussion that I had on stainless steel was interesting and you could understand what makes stainless steel, what are various grades of stainless steel. 300 series is austenitic, so 321, 347 are stabilized grades, 316, 304, these are all austenitic. 410, 420 is martensitic, 430 is ferritic, and then austenitic is 300 series, and duplex is where you have got austenite and ferrite out. This is a little bit about stainless steel. So what kind of welding can be used? Well, today the technology has advanced, so you get stainless steel electrodes for using. You can use TIG welding, gas tungsten arc welding, very commonly used. And gas tungsten arc welding is non-consumable. Tungsten electrode and you have got the fillers. So stainless steel welding can be done by TIG welding, can be done by shielded metal arc welding, and electrodes are there. And how to select those electrodes is a different discussion. We'll do it on some other session. So try to remember, and I'll be more than happy to receive your call and your questions. Until then, goodbye. Thank you so much.